So my name is Stefano Luzzatto. Some of you I know already. Some of you I've not met before. So I think I want to take now 5 or 10 minutes at the beginning of this class just to introduce ourselves and to discuss a little bit the way it's going to work. So I see Luba and Luba, Yunus, Milmukshin, I know, Junaid, right? I'm not sure if we met personally, but we have exchanged some messages. And 2 other participants, Ling Min Hao. Ling Min, you're there?
Yeah.
Hello.
Hello.
And Rahama, is that correct?
Yes.
Is that how good way to pronounce your name? Rahama?
Yes.
Okay. Very pleased to meet you, Rahama.
Pleased to meet you too.
Okay. So this is the course on dynamical systems. And I know that some of you already have actually quite some experience in dynamical systems and some knowledge of dynamical systems. I believe that most of what we've done will be new anyway to you, not because it is necessarily sophisticated, but I hope that we will be taking a path that might be a little bit different. Although, of course, for those of you who are more familiar with dynamical systems in the beginning, some of the concepts will be easier. So I ask you to be a little bit patient. Although, as I've mentioned to some of you that I've spoken to, sometimes there's, especially in dynamical systems, I think always in mathematics, but there's even in very simple things, there are often some very small details, subtle details, which are important and which can easily seem, you can easily miss if you think this is very easy. So I encourage you all, even in things that seem elementary, to pay attention and focus and try to go deeply, because there's always a little bit more to tell, even in simple things, a little bit more to understand. So I'm from home, as you can see, so I'm not going to use the blackboard because my style of my lectures will be quite interactive. Okay, so it will be probably a little bit different from most of the lectures that you have. I think I want to take advantage of this new system here. Rather than just give you a lecture, I want to have more of a discussion during our sessions. So I will give you some lecture notes that contain, I will publish them, I will send them to you every week as we go along. And these lecture notes will contain essentially everything that is important that I say. They will contain all the formal definitions, all the formal results and the exercises and the proofs. So what I would like to do during our lectures, say during our classes, is more of having a discussion, which is a kind of a guide towards these definitions and these ideas. Okay, so if you want, these are recorded, of course, so you can see these again. So you don't really need to take notes. You can take notes if you want, but you shouldn't need to, because I will give you the lecture notes and you have these recordings. And I think these are really an opportunity mainly for us to, I will also be asking you questions. I want you to engage during the class. I want you to be paying attention. I want you to engage. I want us to have some discussions, because this is where new ideas come from, right? I will also be paying particular attention in this class to the processes, that the strategies that you use for understanding mathematical concepts and for understanding this material in general. So I will also talk about, I will use this as an opportunity to talk a little bit about how you do mathematics and how you study mathematics in general, right? So mathematics is a bit of a exploration. Okay, mathematics is like going into the jungle that you don't know and you explore, right? And sometimes you have to fight your way through the jungle and break down some trees. And I will be there as a guide, but it's you who has to do the exploring, right? So it's also your responsibility to look around and ask questions and be interested and say, okay, wait. It's not just me creating a path and you following me in my path, right? It's also about you asking questions and being protagonist of this learning experience. Okay, this is my philosophy. I'm sorry for this little mini lecture, but just so you understand a little bit of the style in which I want to do things. So sometimes maybe in some classes, I will even ask you to do a little exercise or maybe even to get into groups of 2 or 3 and talk about things for just a few minutes. Maybe in the next lectures, we will do something like that. Okay, so before we start, also, let me ask you, have you, in your other classes, have you used the Moodle platform?
Yes, we use it in algebraic topology. It's actively used, the
Okay,
ICV model.
okay. And you find that useful? It works well?
Yes,
Yes.
it worked well so far.
Okay, so what I was thinking also is of trying it. It will be my first experience for me using Moodle, but I was thinking we could try and I will upload the exercises and the material, also the recordings we can upload on Moodle and we can try to see together how it works. So it can be a way that we can communicate together. Are there any general questions, organizational questions about the course? No?
When does the tutorial begin? Does it begin this week?
Okay, that is a very good question. So the tutor will be Doug. He's a visitor here at ICTP for a few months, and I am not sure how many tutorials we should have. How many tutorials do you usually have for the other courses?
About 5, I think.
Okay. Yeah, so I think we will start the tutorial next week. I think possibly Wednesday afternoon. Is that a possibility for you in terms of I will talk with Patrizia and discuss the schedule and we will slot it into some time. Okay. So we will have one tutorial on probably next week on Wednesday and then maybe one a week for 5 or 6 weeks or however long it takes for the course. And I will try to give a exercise sheet every week, probably, or every week or every 1.5 weeks. I will give an exercise sheets. At the moment, I don't have the plans that the exercise sheets should be given for credit, that they should be marked, but you should clearly try to do all the exercises. It goes without saying, the exercises are an essential part of learning the material. And so during the tutorial, you can always ask me questions about the exercises, and certainly during the tutorials, you can talk about the exercise. I guess that's the same way you do in all the other courses. Okay, so let's see. I'm going to share my tablet. So Mubarak is also sitting in. I think Mubarak is my PhD student. Maybe some of you know him already. I think, hello Mubarak. And he will just be listening into the course. So let me share my screen. Yeah, my iPad. sorry, just a second. Yeah. Okay, I guess you can see the screen now. Okay, so let's start with the really very, very, very basic and very simple idea. So we're going to study, this course is a course on dynamical systems. So we will start with, the course will be divided into 3 big blocks, okay? So the first block will be really a collection of basic examples, because dynamical systems is built very much on examples. It's a very sophisticated theory, but it is really fundamentally built on examples. So these are really important. And then the other 2 parts will be more systematic theory, and this will be a topological theory, and then a statistical theory. This is sometimes called ergodic theory of dynamical systems. And these are the 3 big blocks. So each of these will consist of several lectures. And the basic examples, we will really go into some detail, because the basic examples really constitute the fundamental building blocks of the theory. So what is the simplest, also, rather than introducing a lot of abstract notation, I will introduce some general definitions as we go along, depending on the examples. So first of all, let me say what the simplest kind of dynamical systems are. And first of all, let me remind you of the basic picture that I'm sure you're all familiar with, where you have 2 sets, x and y, and you have a function f from x to y. And I'm sure you all remember some basic definitions. So here you have some point x, and it maps to some point f of x here, right? And I'm sure you all remember some basic notions like injective. What does it mean that this function is injective?
One.
One.
What does 1 to 1 mean?
Yes, it takes 1 point to 1 point.
As opposed to?
Don't coincide 2 different points, images of 2 different points.
Exactly. So it means that if you have another point here, x tilde, it cannot go to the same point, right? It goes to a different point, f of x tilde. And surjective, what does surjective mean?
Range is equal to codomain.
Exactly. So it means that any point here that I choose, I can find some point here that maps to it. Okay. And bijective means that it is both injective and surjective. Okay. So this is just a standard notion. Now the fundamental, simple, crucial idea of starting point of a dynamical system is the case in which x equals y. So if x equals y, it's just a simple idea, but it makes a lot of difference. So it means that we have our set here, f, and we can think of this map from x to itself, right? So these are 2 copies of x. So we can write it initially as x goes to x, okay? But of course, if you take a point x here and you take its image f of x, then this is also a copy of x. So really we can draw the same image in this way. We can think of the set x here. This is a map from x to itself. And then you take x, it maps to f of x, which is part of the same set. And because it's part of the same set, we can apply f again to this point. So we can take now this point as the new point, and we can apply f again, and we have f of x. And then we can do it again. And so this is a very simple idea, but it is really quite fundamental, and it has dramatic consequences if you want. So we can iterate. If f map x to x, we can iterate. So we can define, if we take x0, we can define x1 is the image of x0, and then we have x2 is equal to the image of x1, but of course this is also equal to the image of f of x0, so this is f2 of x0, right, where f2 is just the composition of f with f, okay? And then we can generalize this, and we can just have xn is equal to f of xn minus 1, which is just fn of x0, right, where fn is just the composition of f with itself n times. So what we do when we iterate this n times is where we get this sequence of points, right? So we have our x, we have x0, it goes to x1, it goes to x2, it goes to x3, sorry, my handwriting is not very good, and so on. And so we can define the forward orbit of x0 like this. Where xn is just the iterate of x0. Okay, so this is the evolution. This is the first and most fundamental definition of the whole course. It's a very simple definition. It just comes from the fact that you have a function from a space to itself, and then you can iterate it, and that means that you can keep going. Every time you take one initial condition, and we just apply it over and over again, and we get the orbit. Okay, this is what we mean by a dynamical system, is when you compose a map with itself. This is one example, the most, in some sense, the most basic and most fundamental example. And this is also the goal. What is the goal of the theory of dynamical systems? So the goal is to describe in some way the orbits of different initial conditions for different dynamical systems. Okay, this is very simply put, but you need to keep this in mind throughout the whole course. It's so here I have talked about an abstract setting, and we will look at lots of different examples. We will start now at looking at some examples, so it will become much more concrete. But really the idea is whatever example you have, you look at the orbits, and the reason I put this describe here is because, of course, there's many different ways to describe, as we shall see. As we develop more and more sophisticated examples, we will describe more and more sophisticated ways of describing the orbit, right? And then there's lots of questions we want to know. We want to know, for example, does this orbit change if you change the choice of your initial condition x0? Does it change just a little bit? Does it change a lot? What happens if you change the dynamical system? So there is many questions we ask about the structure of these orbits and how these orbits change if you change certain aspects of the system. Okay, so before finishing this very basic introduction, let me say, of course, why did I call this the forward orbit? So if the map F is a bijection, right? If F from X is a bijection, then there is a complete matching, so we can define the inverse, right? We can define what's called the inverse map, which is also a map from X to X, and it is just the map that maps back to the original point, right? So F minus 1 applied to F of X is equal to X. And similarly, F of F minus 1 of X is equal to X. So it's just the inverse. So if you have, this is true in more general, if you have our map, in this case, we have the same X, we have F, so X maps to F of X, right? And then the inverse will map F of X back to F of X. So it's well defined. If it's not injective, then the inverse is not well defined because you have two choices or you have several choices for the inverse and you don't know what to choose. So in that case, we can also iterate the inverse, right? We can write F minus n of X naught is equal to F minus 1. We can compose F minus 1 of X naught, and we can write this as X to the minus n, right? So this is a little bit like saying, okay, we start with initial condition X0, we go forward X1, X2, X3, and so on. We look at the orbit, but then we can say, okay, but this point X0, it comes from some point, right? It is the image of some other point. So what is the pre-image? Where does it come from? It comes from X minus 1, right? So this is all under F, right? And this is under F minus 1. And then there is some other point here, X minus 2, which maps to X minus 1 under F, and X minus 1 maps to minus 2 under F. And here also you have the inverse map in each of these cases. So then we can define the full orbit of X0 is just the orbit of X0 is equal to Xn for n in Z. So this is the forward and backward orbit of this. Any questions or comments so far? Okay. So let's start with the most fundamental examples. And we're going to start talking about maps. So let's talk about fundamental examples. Let's start by talking about maps from R to R. So this is the simplest map. So this is the most familiar setting, right? Maps from the real line to the real line. So what would be the simplest possible map that you can imagine that we can study from R to R? If you were we're just given this basic framework, we want to choose a map just to start seeing what happens to the orbits. What map shall we choose?
Identity.
Quadratic family, a quadratic function maybe.
Identity quadratic function. So this is example F of x equals x is the identity. F of x equals x squared is the quadratic function that Milmokshin is saying. But I think f of x equals x is a little bit simpler, right, than x squared. Let's really stick with something that is simple as possible. So what is the dynamics of the identity map? So this is the real line. What is the orbit? We start with some initial condition x0. What is f of x0?
All points fixed point.
Every point is a fixed point, right? So what does it mean, fixed point? So in this case, because it's the identity map, x1 is equal to f of x0. And of course, the same is x2. x2 is equal to f of x1, which is equal to f of x0, because x1 is equal to x0, which is equal to x0. And the same is true for every point. xn is equal to x0. So the orbit, the forward orbit of x0, which we will always define as there's a little bit of ambiguity here because we define the orbit as a sequence. It will be useful to define it as a sequence, the forward orbit. But of course, it is a sequence, but it is the constant sequence, right? So in fact, all these points is just a single point here. Right? And in fact, in this case, the map is also invertible, right? Because the identity map is a bijection. And so we have that the full orbit is also just a single point, x0. So, oops, sorry. I don't know what happened. Hang on, let me just stop sharing here and try to get back in. Okay. Okay. So we say that x0 is a fixed point if f of x0 equals 0, equals x0. It's fixed. So for the identity map, for the map f of x equals x, every point is a fixed point. This is simple. Okay, let's take this one little step further. Let's suppose we take the map f of x equals 1/2 of x. So I would like to hear a little bit from the students who I don't know if you have so much background in dynamical systems. So Junaid, Rahama, Ling, and sorry, we have a new student here. What is your name? I cannot see your name. Are you there? Is anybody there?
Yes, we are.
Sorry?
Yes, we are here. We can hear you.
Okay. Now I see your name. Okunola Toluwani.
Yes,
Is that right? How should I call you? Toluwani or Okunola?
Toluwani.
Toluwani. Very nice to meet you.
Thank you.
Toluwani. Okay, so Toluwani, Lingmin, Rahama, Junaid, I kind of would like in these first couple of lectures particularly to hear from you because Younes, Ruba, and Milmukshin already have quite a bit of background in dynamical systems. So for the first few lectures, I want to make sure that we're going at the speed that is suitable. I'm going slowly, so I'm sure it's okay. But I would like to get some feedback from you about how it's going, right? So if you can, participate in the conversation, it will help me to understand, if there are any problems. So let's think about this map here. F of x equals 1/2 of x. What can we say about this map here? Suppose we have here the real line and we choose some point x0. What happens when we apply the map F? Where's x1?
It converges to 0 in the end.
Exactly, right? So this is quite clear to see. So this is x1 will be 1/2 of x0, and then x2 will be 1/2 of x1, and so on, right? And the same thing if we choose some x0 negative, right? Because you just come closer by 1/2 each time. So where did we use the fact that it's 1/2? Can we use a different coefficient for x and get the same kind of behavior?
For any n, I think it is the same.
For any n, okay, let's say that we have f of x, because we're using n for the iteration, so let's call it a of x. So let's try to study systematically the different possibilities that can occur for different values of a, okay? This is the map that we're going to spend a little bit of time studying, the family of maps, right? Depends on a. So now we chose a equals 1/2, and we saw, what did we saw? We saw, as you correctly remarked, that xn converges to 0 as n goes to infinity, right? This is very interesting because even though this is a very simple example, so this is the orbit, right? This is the forward orbit of x0 is equal to xn, n equals 0 to infinity. So this sequence converges to 0 as a sequence when a equals 1/2. What about, wait, before we continue, what about 0? 0 is a special point in this case, right?
It's not bijective.
Sorry?
It's not bijective.
What is not bijective? This map?
Yes.
Is it bijective or not? That's a good question. F of x equals 1/2 of x. Is it bijective?
I mean, when it equals to 0, then when the coefficient is 0.
When the coefficient is 0. Okay, when a equals 0. Sorry, I thought we were talking about this case, the case. Okay, so a equals 1/2, we have this. What happens when a equals 0? Then we have f of x equals 0. Is that a legitimate dynamical system?
No, all orbits are constant after one iteration.
Exactly, but that is still a perfectly legitimate dynamical system, right? It is not injective, but it doesn't matter. We still have everything goes to 0, so everything still converges to 0. So you have, if you take any initial condition, it will jump to 0, and then it will stay in 0, right? So 0 is a fixed point. And for any x0 in R, we have that xn is just equal to 0 for all n greater than or equal to 1. In fact, for all n different from 0, even for yes, this is not bijective, so we cannot go backwards, so we cannot define the backward orbit. So we have this for all n greater than or equal to 1. Okay, which other values of A would it be interesting to study?
-1, bigger one.
I want to hear from Rahama, from Junaid. It's an interactive class. Sorry about that. You need to participate.
I think for when A is greater than 1.
What happened when A is greater than 1? What was your statement?
When A is greater than 1, I think it's interesting to check.
Okay, what happens when A is greater than 1? Let's see. What happens? What happens when A is greater than 1? So what shall we do? Shall we choose a specific value, or do you want to just do it in general?
We can pick a specific value, say A equals 2.
A equals 2, perfect, okay. A equals 2. So what happens here? x0?
Yeah, we have 2x0.
Exactly, so it becomes bigger, right?
Yes,
x1, maybe that's too big here, x1. So x1, so x1 is equal to 2x0, x2,
4x0.
yes, 2x1, which means 2 times 2x0, which means 4x0. x3 is twice that, all right, so this is 8x0. So what's the general formula?
2 raised to power n x0.
Exactly, right. So you can see here that what you're doing is you're just multiplying by 2 each time, yeah?
Yes.
So can we generalize this? Now we chose, so here we have xn equals 2 to the power of n x0. So, so what is this doing? This is going, is it converging to 0? What is happening to this sequence here?
Divergence to infinity.
diverges.
Exactly, it's diverging to infinity. Right? It's going further and further away towards infinity. Is this map bijective for A equals 2?
Yes, it is.
It is bijective, so that means we can go backwards as well, right? So we can define x minus 1, which is equal to f minus 1 of x0. What is f minus 1 in this case? In other words, where does the point x0 come from? What is the point that maps to x0?
x0 over 2.
Over 2.
Exactly, right? Because if we take here x0 over 2, of course, when you take x0 over 2, you multiply by 2 and you get x0. That's what the map does, right? So this is equal to 1/2 of x0. And then you can easily see that x to the minus n is equal to 1 over 2 to the n x0, right? Because each time you half, 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 half. So this is converging to 0, right? 1 over 2 to the n x0. So interrupt me if you get confused or if you're lost at any point. Can we kind of generalize this? So what is the, if X, what would be, how do we generalize? Do we want to try A equals 3, A equals 4, or do we understand now what's going to happen for these values of A?
So if A is greater than 1, then it diverges to infinity.
And how do you see that?
Like same dynamics as in this example.
Very similar, right? So in this case, if we have, in fact, let me point out, so of course, if the map, so in the general case, f of x equals ax, that's why this is a particular simple map, because we have that x1 is equal to a of x0, x2 is equal to a of x1, which is equal to a of x0, right? Because that's what x1 is. So you multiply by a every time. So this is just a squared x0. And then x3 is equal to a of x2, which is equal to a times a squared of x0, which is equal to a cubed of x0, and so on. Right? So you get a xn equals an of x0. Right? And then, of course, the inverse of this map. Okay, so let's just look at that. So here, in terms of the forward orbit, we can immediately see this is the general form for the nth image of this initial condition. So then it becomes easy to see what happens if a is bigger than 1. This implies that a to the n goes to infinity, diverges to infinity, right?
Yeah.
If a is between 0 and 1, an goes to 0.
Yeah.
What about if a equals 1?
A converges to
Identity, we have seen it.
That's right? So a equals 1 corresponds, so it's just a to the n is just equal to 1. So indeed, it's the same case we had. So in that case, we just have xn equals 0, equals x0, right? Because it's just a to the n is that. What if a is negative?
Negative infinity.
A
So-
is less than -1.
Okay, so let's suppose a is less than -1.
Yeah, then it is going to minus infinity.
Is it?
No,
Doesn't
it is just the reverse of the above system.
Is it?
Yeah, positives will go to the negative infinity and negative numbers will go to positive infinity.
Is that so?
No, I don't think so.
What happens then?
It doesn't seem to follow a particular pattern. It diverges, but
Okay, so let me interrupt you here and use this as an opportunity to point out a really important point about how to study. Okay, I will try to use these words because they're very important. So as you see, this is a very simple example, but there's not completely obvious things going on. So what did we do? How did we approach? You see, I wrote this map right from the beginning here, right? So what did we do before we started trying to understand the general phenomena? We tried an example, right? We tried a equals 1/2. Then we tried a equals 0. So this process is called specializing. right? So this is something that I'm sure many of you are familiar with, but I will just write it here because it is an important, I will use this terminology a lot, specializing. So often when you are trying to find your way in the jungle of mathematics, right, as we said before, you specialize. Specialize means do some simple case, the simplest possible case. So you're trying to understand something. So here, for example, we take a minus 1, and your initial reaction is, well, okay, so this is like this. They say, well, wait a second, actually, it's not so obvious. You multiply by -1, what's happening, okay? So let's specialize like we did before. Let's choose a specific case. For example, a equals -2, for example. And let's choose a specific initial condition. Okay, let's not jump to conclusions about what's going to happen. Although those are very interesting conjectures, I want to emphasize that what you were saying before, you were making conjectures, okay? Conjectures is also a very important part of the mathematical process, right? So I'm not saying that it was not valid what you were doing, quite the opposite, it was very valid. You're saying, okay, everything converges to infinity, minus infinity, plus infinity, these points go here, these are conjectures, okay? And it is useful to make these conjectures, and then you have to test your conjectures, okay? You test your conjectures by specializing and looking at some examples and trying to understand what happens. So what happens to this x0? What is x1?
It's jumping here and there.
It's jumping here and there. What do we mean by it's jumping? Let's see. So x1 is minus 2x0. So where is minus 2x0? This is, so if x0 was positive, as in this picture, then I would, minus 2x0 is negative. So we have here minus 2x0 because it will be twice the distance from 0 than x0, right? It's minus 2x0. What is x2? Yes, what is x2?
4x0.
4x0.
Exactly, because it's minus 2 times x1, which is equal to minus 2 times minus 2x0, x0, which is 4x0. So it's back here on the other side. So this is x1, and x2 is here. Okay, so maybe I need to draw a bit of a larger scale. So here is x0, and it maps to some point here, x1, which is twice the distance. And then now this one will map to twice the distance here, x2, right? And then x3 will be minus 2 x2. So it will now be somewhere. So you look at the distance between 0 and x2, and you go somewhere here. This is x3. Okay. And you start seeing what happens, right? At this point, we now see what's going to happen. I think it's clear. It will go here, x4, then it will go here, x5, and so on. So what is happening to this sequence xn? Is it converging to something?
No, it diverges.
Yeah, I mean, it's diverging in a particularly strange way, right? In some sense, it's not even diverging. We cannot say, I cannot say that xn is diverging to plus infinity or to minus infinity, right? Because it keeps jumping back and forth. It's very crazy. What I can say, for example, is that the absolute value of xn is going to infinity, right? Because the absolute value is getting bigger and bigger. Good. So that, as you can see, in fact, we can see that after we've done this specializing, right? So you get some idea from a special case, then it is clear that this is going to happen in every case, right? If you take a to the n x0, if a is negative, taking powers over negative numbers, they will alternate between positive and negative, right? So it's clear what happens. So if A is between -1 and 0, then what is going to happen there?
Then
A
it
minus
will
half.
convert to 0.
That's right. So if you have -1/2, it's good, and -1/2 or any A between -1.5, the absolute value of A is less, so it will get closer to 0, but it will jump, right? So x0 will jump to x1, and then it will jump to x2, which is closer, and then it will jump to x3, and then it'll jump to x4. Okay, so you can see that this will happen for A equals 1/2, but it will happen for any A between -1 and 0. So can we say in this kind of situation, can we say that xn converges to 0 as n tends to infinity?
No.
Yes, we can say.
What is the definition of convergence of a sequence? So this is a sequence. Do you remember the definition of converging sequence?
You can find an n such that after that n, every will goes to that point.
Exactly. Okay, so if you are, let me say that this converging sequences and subsequences and so on will play a fundamental role in what we're doing. If you need to go and revise a little bit the theory, do that. But because we will use them a lot to understand what's going on. So here we have that everything is getting close to 0. And as Ling said, for every neighborhood of 0, after some time, you're always in this neighborhood, right? If you take the sequence xn, as you can see from this picture, it is getting closer and closer to 0. So this is not usually this jumping to both sides is not something that you're used to imagine when you think of a converging sequence. You think of the converging, it should converge in a more kind of monotone way. But this is still satisfies the definition of a converging sequence, right? Because it gets closer and closer to 0, and for any neighborhood of 0, after some time, once you fall inside that neighborhood, you will stay in that neighborhood forever. You can take a smaller neighborhood, you will stay in that neighborhood. Okay, so we can say that this holds, even though it does so by jumping back and forth. Okay, have we looked at all possibilities? Is there some value of A that we have not looked at?
Equal to -1.
Minus
Excuse me?
Is equal to -1.
Exactly, equal to -1. This is an interesting case. What happens when A is equal to -1?
It's oscillating but never going to out anywhere.
Never going anywhere? That's a good way to put it. It's oscillating but never going anywhere. Let's see what happens. So 0 is always a fixed point. If we take x0 here, oops, I don't know why this keeps shutting down. Sorry, I have to stop sharing again for a second. Because yours, you cannot see it, but my screen went black. I don't know why. And okay, let me share the screen again. Okay. Yes. So you've had time to think a little bit. What happens when A is equal to -1?
I have just minus x naught.
Exactly. Minus x naught. So here is x1. And what about x2?
X naught.
Exactly, right? So x2 is equal to minus x1. which is equal to x naught. And then x3,
minus x naught,
which is
minus x naught.
It is minus x.
x1,
Oh, yes.
Yeah.
right? Which is x1. So you're right. So it's x naught. So what it's doing is jumping back and forth between x naught and x1. Okay, now this brings us to our second most important definition. So what we have here, if we look at the orbit of x naught, this is of course always an infinite sequence. But in this case, this infinite sequence is constituted by how many points? How many distinct, geometrically, how many distinct points?
2 points.
2 points, right? So in fact, even though you have an infinite sequence, you still have 2 points. This is constituted by x0 and x1. So this is called a periodic point. So we have the definition. If the x naught is a periodic point, if there exists some k greater than or equal to 1, such that fk of x0 or xk is equal to x0. Okay, k is a period. K equals the period of x0. So when a equals 1, every point is periodic of period 2. Okay?
Sorry,
Yes.
a equals to 1.
Okay. What happens when a equals to 1? We have the identity map. And
The-
then,
Period of 1, right?
exactly, that is a good observation, Lynn. So if a point is a fixed point, is a special case of periodic point with period 1. Right? When k equals to 1, then f of x naught, f of x0 equals x0, and then it's a fixed point. But notice something a little bit curious here, right? So that a fixed point also is a periodic point of period 2. Is that true? If x naught is a fixed point, then it is actually periodic of any period. Right? So, and if a point is periodic of period 2, they're also periodic of which other periods? Sorry?
We should choose the smallest one, right?
Right. So it is true that a fixed point is a periodic point of every period. A periodic point of period 2, is someone trying to say something? Or?
So periodic, I think, for even values of k.
Exactly. If it's periodic of period 2, then it is also periodic of period 4, because it just comes back, right? If you apply twice, it will come back. If you iterate 4 times, it will just keep coming back every 2, right? So if it is periodic of period k, then it is periodic for every multiple of k also. So this is, we do use this definition, but to avoid confusion, we also talk about the minimal period. So x0, so sometimes it's useful to say x0 has minimal period k greater than or equal to 1 if k is equal to the minimum. Wait, let me see exactly how I wrote that. Minimum of I greater than or equal to 1 such that fi of x0 equals x0. This is the minimal period. Okay, so this is clearly, so in that case, a fixed point, we say that a fixed point is periodic of any period k, but its minimal period is 1, right? And these periodic points of period 2 that we have here, they are periodic of every period 2 to the k, 2 to the k, but its minimal period is 2. Okay, so I would like, usually I like to take a little break halfway through, or okay, we've gone a little bit longer because I think it's hard to concentrate for 1.5 hours. So let's take now a 5-minute break. Okay, so we would take 5 minutes. So it's 3:05, so at 3:10. Okay, so you can switch off, relax your minds for 5 minutes, go and get a glass of water, whatever, and I will see you in 5 minutes. Okay?
Okay.
Okay. See you later. Again. Okay. Good. Everyone back?
Yes.
Okay. So
Yes.
okay. So what have we, let's review a little bit what we've done so far. So we have done quite a systematic study of the family of maps AX, right? We've really looked at essentially all the possibilities. So this will be, I want you to do this. One of the exercises I will give you will be to do this. And in fact, we will generalize it even a little bit more now in the rest of the class. But first of all, we have studied this, and we have also studied some kind of points. So we have seen fixed points. What kind of, remember what I told you, what is the goal of dynamical systems? The goal of dynamical systems is to describe the orbits. Okay, this is what we've been starting to do, like describe the orbits. So what do we mean by describe the orbits? So far, we have seen some special kind of orbits. For example, we have seen fixed points. We have seen periodic points. Of period 2. For the moment, we've only seen fixed points and periodic points of period 2. What other structure have we seen of orbits that are not, what about points that are not fixed and are not periodic? What have they done? What kind of things have we seen? I cannot hear you.
Converge to 0.
Exactly. Very good. So we have seen points that converge to 0. We have seen points x0 such that xn converges to 0. Now, in these examples, when these converge to 0, what does 0 do?
0 remains fixed.
0 is a fixed point in this case, right? In fact, for this particular map, 0 is always a fixed point for every A, right? So the fact that they converge to 0 and 0 is a fixed point leads us to an interesting definition, which I think now is a good moment to introduce it. Definition, we say that a fixed point. So, sorry, before I write this definition, let me say that when I give these general definitions, I think it will be useful. Now we're looking at these examples as a map F from R to R, but a lot of these definitions work right at the very beginning. I just said you take some set X and you take a map X to itself, right? So the definition, for example, of fixed point and periodic point applies to any set X. It does not need to be the real line or anything like that, right? It's a fixed point, it's a fixed point. Now, the fact that something converges to something else needs a little bit more structure. What structure do we need to be able to talk about convergence?
Topology.
Exactly, right? So we need X to be at least a topological space, right? So from now on, or a metric space. A metric space, of course, is a stronger metric space, implies it's also topological space. So I think now, whenever I make general definitions, I will always assume that X is a metric space, just for simplicity. Always assume X is a metric space. A lot of the definitions also work if X is a topological space, and some stuff that we're going to do later will need more, like the real line has much more structure than just a metric space, but many of the definitions just need X to be a metric space. So definition, we say that a fixed point P in X is an attracting fixed point if. So how should we say? So what I want to, the idea of an attracting fixed point is that if I take some points nearby, they will converge to P. So what I want to say is an attracting fixed point, a little bit like the example we saw of 1/2 of X, is if there exists a neighborhood U of P such that Xn converges to P for all initial conditions in this neighborhood. So does this hold in the examples that we had before? Suppose we had f of x equals 1/2 of x was one of the example, right? So 0 is a fixed point, and we already know that if we take an initial condition x0 here, it will converge to 0. If we take an initial condition here, y0, y1, it will also converge to 0. Okay, so in particular, if I take some neighborhood of 0 here, then every initial condition will converge to 0. In fact, in this particular case, it's a globally attracting. So we say that P is globally attracting if we can take U to be the whole space X. So every point its orbit converges to the fixed point. So P is a globally attracting. Everybody wants to be there, right? It's like there's something exciting going on and we go there. Globally attracting. Good. So what else have we seen? We've seen some fixed points. We've seen periodic points. We've seen attracting fixed points. What happens if f of x is 2 of x, and then 0 is not an attracting fixed point, right? What happens is that points move away. They move away from 0. Yes, sorry?
There is a mistake in the writing. I think f of x is equal to 2x.
2x, yes, thank you. Thank you. So in this way, we will say that P is a repelling fixed point. So P is a repelling fixed point. How should we explain, how should we formalize the idea that the points are moving away from the fixed point? How can we give a formal mathematical definition of this idea? Because this is what's happening here, right? If you take 2x, you take a point, even if you take a point that is very close to 0, to the fixed point 0, it is moving away. How can we say that?
For any neighborhood.
For any neighborhood, what happens?
There should be a case such that fk of that point is not in that neighborhood.
Exactly. Exactly. So for all sufficiently small neighborhoods, right, or there exists a neighborhood. So for every arbitrarily small neighborhood, because if you take the whole real line as your neighborhood, then this does not happen, right? If you take the whole real line, then the points will stay in the neighborhood all. So if for all sufficiently small neighborhoods, U of P, there exists some k greater than or equal to 1, such that xk equals fk of x0, such that, there exists a neighborhood U of P such that for all x0 in U, there exists k greater than or equal to 1, such that xk equals fk of x0 is not in U. Okay, this is the idea of a repelling, so points are moving away. Okay, so there is one more kind of point that we have seen in this family that is not fixed point, is not attracting, is not, well, there is, okay, maybe it's hard for me to say. So there is a special kind of attraction. Remember in the degenerate case when f of x equals 0, remember what happens to these cases. This is 0. We take x0. Is x0 is not a fixed point? Is it a periodic point?
Yes, of period. No.
It's not periodic because it never comes back to itself. But it still has a very strange behavior, right? Because it maps to 0 and then it stays in 0. So it's not a fixed point, it's not a periodic point, but after some time, it lands on a fixed point. And then it becomes fixed after some time. Okay, so this we call it, we say that X0 is pre-periodic. If there exists K greater than or equal to 1, such that Xk equals Fk of X0 is periodic. So this is an example, right? And we will see lots of other examples in other situations in which you have a point that never comes back, but after a while it lands on a periodic orbit and then it goes in a loop. It stays in the periodic. Like in this case, X0, after one iterate, it maps to 0, and then 0 is a fixed point. Right? So if you want to draw this schematically, you can have here a fixed point, and then you have a point X0. This is fixed, so that f of p is equals to p. And then X0 maps to p. So p is equal to f of X0. In this case, X0 is a pre-fixed or pre-periodic, right? More in general, you might have a situation where you have a periodic point. So here you have, for example, P1, P2, or let's say P0, P1, P2, and then it comes back to P0. So here we have a periodic point of period 3, and then we have another point X0 after one iteration or after some number of iteration. It maps onto P0, and then, of course, it becomes periodic. So it moves around, and then it lands on a periodic point, and then it starts going around and around in a loop. It's a periodic point. Okay, so before we finish, I'm going to tell you what an important exercise that you should do, first of all, is to generalize, right? So we have been studying these maps, f from R to R, given by f of x equals ax.
Excuse me, Professor.
Yes.
Could you please explain the schematic diagram for periodic?
Okay, so imagine you have, so let's forget about this for the moment. Imagine we have a periodic point. Do you agree that this is a periodic point here?
Yeah.
Okay, so a periodic point means a point that after some time comes back, right? So in the examples we've seen so far, we've only seen period 2, right? But in some other examples, we will see period 3, period 4, we'll see many different periods. So it's a periodic point. Now, you can have some situations if the map is not injective, because if the map is a bijection, you cannot have any pre-periodic points, because if the map is a bijection, then the only point that maps to P0 is P2. You can go backwards and forwards if the map is a bijection. If the map is not a bijection, you might have several points mapping to P0, for example, right? Including, you might have a point here that maps X0, X1, X2, and then maybe X2 maps to P0.
Okay.
And so what is the orbit of X0 in this case? So the orbit of X0 is, as always, we start by recalling that the orbit is, first of all, a sequence. So this is sometimes a little bit delicate because we will think of the orbit as two things. And in mathematics, sometimes you need to think of the same object in two different ways, right? And it will be important to use it because sometimes you need to think of the orbit as an infinite sequence, which is this, right? It's always an infinite sequence. So given any point, you can take the infinite orbit, but this infinite sequence sometimes consists of a finite set of points, right? For example, geometrically, if the point is fixed, it's still an infinite sequence, but it's the constant sequence. Okay, and so in this case, what is the actual points that constitute this orbit in the case in which I drew in the picture?
X naught.
Not S1, S2, P not P1, P2.
Exactly. And notice that this is not a periodic orbit because you never come back to X naught, right?
Okay.
You go from X naught to X1, from X1 to X2, from X2 to P naught to P1, P naught to P2, P1 to P2, and then P2 comes back to P1.
P naught.
So then you have P naught, yes. And then you have the loop here made of 3 point. So this is called a pre-periodic point.
Okay.
Just maps. It's pre-periodic because it has a life before being periodic. It's like before you go to school, you have a life before, and then you start going to school and you get lost in the loop. Okay, so we have studied systematically, and this is an important point, right? An approach that we will try to continue throughout. This is, in some sense, a very simple family. It's just the linear maps from R to R. You're very familiar with the graphs. I'm sure you know how to draw the graphs for every A, yeah? But as you can see from a dynamical point of view, already quite a lot of things happen, right? As you change A, sometimes it's the identity, every point is fixed, sometimes everything converges to 0, sometimes everything goes to infinity, sometimes things jumps up and down, sometimes you have a pre-periodic to 0, so you have quite a lot of things even for this map. Now, what is the simplest possible way you can think of pushing, of studying a maps just a little bit more? If you know these maps, what is the next map that you will say, okay, what happens there?
Quadratics.
So quadratic is one step, but there is something that is simpler than quadratic. There is still linear.
Translation.
Translation. So what maps? What would be, how will you write the maps?
AS plus E.
Exactly. So let's just spend a few minutes looking at this map now, okay? And then I want you to think about it at home in this way, the similar way to which we've analyzed A of X. So maybe let's specialize again, right? The simplest case, let's suppose A equals 0 again, which means that we just have f of x equals b. What happens here? F of x equals b.
It's pre-period.
Everything maps to b, right? So b is a fixed point, clearly, because f of b equals b, because everything equals b, and everything else just maps to b. So it is exactly very similar to the case we did before, f of x equals 0. B is just another constant. Everything maps to B. Everything is pre-periodic. B is a fixed point. What about f of x equals x plus b?
It's moving away and
A is positive.
further.
It converges to infinity.
Yes, both of you are correct. So we have here x naught, right? So x1 is equal to x naught plus b.
Mm.
Are we thinking of b as being positive or being negative? Let's think of b as being positive, just to try things out, right? Simplest. So we just, x1 is this, so this is just b. We're adding b. What is x2? Is equal to x1 plus b. So we have x2. This is also distance b. So this is just x naught plus 2b. Right? So in fact, this is easy here. You can just have xn equals x naught plus nb. We have a simple, so this is just translation, as you said. So we have x0 here, and then we just jump by b each time. It's a little bit different from before, right? Before, when we were diverging, if we take, for example, f of x equals 2x, then we are doubling each time. So that is moving away exponentially fast, right? Here we're just translating b, 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 b. We're moving much slower. We're just moving by little steps of b at a time. But still, we're going, and also in the case f of x equals 2x, if you were negative, you would go to minus infinity. You were positive, you would go to plus infinity, right? Whereas in this case, what is happening to these points? Everything is going to plus infinity.
Mhm.
All the points are moving, even the ones that come from minus 2 million, right? And they're just slowly, one step at a time, they're moving forward and going to plus infinity. If b is negative, they will just be moving in the other way. So does this have any fixed points? Are there any fixed points here?
No.
No.
No fixed points.
No.
Exactly. So this is a map without fixed points. This is a new phenomenon in terms of the ones we're looking at before, right? So f of x equals a of x, ax. It always had 0 as a fixed point, and then we had other dynamics happening for other points. Now here we see an example with no fixed points. So what is going to happen now? Let's see if, for example, we take this. Let's choose b equal 1, for example. So tell me what is going on in your heads. What are you trying out in your heads? Okay. What is the process, the strategy?
First of all, it is like coming backward to half, and then we are translating 1.
Yes,
And
that's
forward.
right. That's right. So we are, in your mind, you're thinking that when you take half of x, you are coming close to 0. In some sense, you're reducing, but then you're translating with 1. So which of the two is going to win? Is it going to kind of keep getting close to 0? Or is it going to go to infinity because you're adding 1 each time?
First, we find fixed point. It has unique fixed point, and it's attractor, global attractor, that fixed point.
Okay, Mukshin, but you have an advantage here, right? Okay, so so let's it's important. This is the second step, and I think the strategies for studying this are very important. Okay, because we're going to be at the moment. I'm spending a lot of time going slowly through these steps, and then as we progress in the course, I will expect you to be able to apply these strategies yourself. Okay, so Mokshin is correct, but the question is, how did he know? He knew because he knows a lot of other things about dynamics already. So what he said, one point he said is that it's interesting. So one of the things when you don't know what's going to happen, what I want to focus now for the next few minutes, and then we will finish, is how do you even start to study? Okay, so I think it's very natural what Junaid was thinking, okay, I'm trying to think of an initial condition and trying to imagine what it's doing, right? Half of x0 plus 1, okay. So you can try to do that, but it's not so easy to understand what's going on, as you saw, right? Because 0, so first of all, 0 is not a fixed point, right? So 0 actually goes to 1, right? And then, as you said here, you take some point x0, and then you will come close, and then you will translate by 1, plus 1. So you will take, this is half of x0. So you seem to be switching, so it's not clear what's going to happen. So one always useful strategy is to start by asking, are there any fixed points? So if you don't know what's going on, it's always a good question to ask, are there any fixed points? Because the fixed points is simply the most basic and fundamental kind of orbit we can have.
Two.
So are there any fixed points here?
Yes.
Two.
How do we establish the fixed points?
Fs equals to x, an evaluated point.
Right. So a fixed point is defined by the condition f of x equals x. This is what it means to be a fixed point, right? So in this case, we have this formula. So what this means, f of x, it means that we want half x plus 1 to be equal to x. So if we find an x that satisfies this condition, then it will be a fixed point. Let's try to calculate this. So this is a simple, this we can calculate easily. So we take, this is 1 equals x minus 1/2 of x, right? So this is 1 equals 1/2 of x. So this is x equals 2. Is 2 a fixed point? Now let's check. So let's put f of x equals 1/2 of x plus 1. So if we calculate f of 2, this is 1/2 of 2 plus 1, which is equal to 1 plus 1, which is equal to 2. So this is now an example. It's still in the world of simple examples, but it's something that was not completely trivial. You know, we could not just look at this unless you know what you're looking for, to look at this and see that it has a fixed point at 2. Does it have any other fixed points?
No.
It cannot have any other fixed points because they must satisfy this equation, and x equals 2 is the only point that satisfies this equation. Okay, so then the question is, what do the other points do if they are not fixed? And judging from the examples that we've seen before, if it's something similar, then you imagine that they're either converging to the fixed point, if the fixed point is an attracting fixed point, or maybe they're moving away from the fixed point. Maybe they are periodic points. So now I'm going to leave you to do it, okay? I think I'm going to leave it to you. I want you to think of this as a puzzle, if you want, or as a problem, not something that you need to look up on Google the answer, right? Or even in the notes or anything. I want you really just to think about it and try to establish for all. So you need to do something systematic. So we want of f of x equals ax plus b. To write down all the possibilities, right? Including when b equals 0, we have the family that we did before. When b is different from 0, all the different values of a and b, in each case to give a complete description of the dynamics, what kind of orbits you get, if you have fixed points, periodic points, attracting fixed points, what do they attract, and so on and so forth. Okay, this is the first exercise. I will put it on the sheet, but maybe I will not post the sheet immediately. So this exercise is to describe all the possible orbits, all the possible dynamics for all AB, all possible values of the parameters AB. You get different systems. And I want you to prove things, okay? So as it happens, so as Mir Mukshin said correctly, in this particular case, the fixed point at 2 is attracting fixed point, okay? It's a globally attracting fixed point. So in fact, this here at 2, you can see that the points, they all, every point on the real line, it converges to 2, okay? But I want you to provide a proof of this, right? You need to convince yourself, you need to convince someone else who does not believe you, which means that you need to justify, to be able to be 100% sure, yes, not just, yes, it looks like, or if I choose initial condition x naught equals 1, then it's converging to 2. You really need to provide an argument that guarantees that this is true. Okay?
Yes.
Okay, so I think that's enough for today. Are there any other questions or comments before we go?
Are you going to share the notes with us?
Yes,
Okay.
I'm going to put them on Moodle.
Okay.
Yes, so it's the first time I use Moodle, so I don't know they will know exactly how to do it. And what I will do is I will share some typewritten lecture notes. So I have all of this stuff typed in a proper way. Okay. If you want, do you want me to share also these notes these handwritten notes?
Yes.
Okay. So I will also share the handwritten notes for you, and I think you have access to the recording of the video.
Yes.
But again, I will emphasize now, and I will emphasize in every class, is that when you're trying to solve the problem, so for example, when you're trying to do this exercise, you can, of course, refer to the lecture notes, refer to these notes, but the best strategy is really just to think about it. Think about it and use these various strategies that we start looking at, to specialize, look at some special cases. And then when you understand this, what happens for A equals something or B equals something, you say, okay, does it also happen for all A's between 0 and 1? Does it happen? You try to generalize and understand how common that behavior is as you change the parameters A and B. So you try to do it. Okay, so I will put everything on Moodle. You can send me an email if you have a specific questions. I'm happy also to reply to emails, but you will have next week, you will have a tutorial. So you will also be able to ask questions in the tutorial, and I will see you on Thursday, right, for the second class. Okay.